Let's review enthalpy. For processes that occur at constant pressure, the change in enthalpy delta H equals the heat transferred, Q. Delta H is positive for endothermic processes and negative for exothermic processes. The change in enthalpy for a reaction depends on the substances in the reaction and their states of matter. For a reaction, the change in enthalpy delta H, sometimes called reaction enthalpy or heat of reaction, is for the number of moles of reactants and products shown by the coefficients in the equation. Here we have a chemical equation. On the right you see a value of enthalpy that is associated with this reaction. It's understood that the coefficients in the equation, namely the 2 in front of the hydrogen, the unwritten 1 in front of the oxygen, and the 2 in front of the water vapor, represent numbers of moles of those substances for this given amount of energy. These proportions that are shown in the equation are used in stoichiometry. In earlier studies of chemistry, you might have done some calculations involving stoichiometry. If we were to put enthalpy in this island diagram, we would put it right there, because from a balanced chemical equation we can relate numbers of moles of a reactant or a product with an amount of enthalpy. So you can see that for any stoichiometric calculation involving enthalpy or energy, sometimes it's just referred to in a question as energy, you only need a maximum of 2 conversion factors to finish your problem. Let's try a couple of examples. At the top of the screen we see an equation for the combustion of methane, and in the upper right corner we see the change in enthalpy associated with the reaction between 1 mole of methane and 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. We can see that this is an exothermic reaction because of the negative sign in the change in enthalpy. What's the change in enthalpy when 54 grams of methane are burned? If we use this island diagram, which you might be familiar with from previous studies, on the left and on the right we have mass, volume of gases at STP, and particles, MVP. It's the same on the far right, MVP. These triangles in the middle represent moles, and they're a different shape for a couple of reasons, the most important of which is that moles are the most important quantity in chemistry. They allow us to calculate many other things. And then down here we have energy. We're starting with grams of methane, which is mass, and we're going to end up at enthalpy. We're going to have to cross 2 bridges, so we're going to need 2 conversion factors to solve this problem. The first conversion will take us from grams of methane to moles of methane, so we need to find the molar mass of methane using the periodic table. Carbon has a molar mass of 12, and each hydrogen has a molar mass of 1, so that's 16. We set this up so the units cancel, and then we need to go from moles of methane to enthalpy. So we need another conversion factor, and according to our balanced equation at the top of the screen, for every 1 mole of methane that's burned, the change in enthalpy is negative 891 kilojoules. Moles of methane cancel, then we'd simply go 54 divided by 16 times negative 891, and we get roughly negative 3,000 kilojoules. But if we're reporting this to the correct number of significant figures, 54 was our given quantity, which has 2 sig figs, so we should report 2 in our answer. Let's try another one. What mass of water is made if 10,540 kilojoules are released? If we go to our little stoichiometry model, we're given the amount of energy or enthalpy, so in other words we're going to start here, and then I always like to proceed left to right, so we're going to end up at mass of water. Mr. B, why can't I go to this mass in the upper left here? There's no particular reason why you couldn't go there if you want that to represent grams of water. But I always like to work left to right. So I'll always start further to the left and I'll proceed further to the right. Here again, we're going to need two conversion factors. One, when we're crossing this blue bridge here, to moles of water, and then we're going to need one to go up to grams of water. It says that this quantity of heat is released, so I'm going to put a negative sign in front of that. Negative 10,540 kilojoules. According to our equation at the top of the screen, there's a ratio. For every 2 moles of water that are produced, we release negative 891 kilojoules. We orient those so the kilojoules cancel. Then we convert to moles of water using the molar mass. Oxygen is 16, each hydrogen is a penny apiece, so that's 18. Round to 4 significant figures, because that's how many we started with, and we're done.